It's 6 o'clock in London, it's 1 p.m. in New York, it's 1 a.m. in Hong Kong, 3 a.m. in Sydney, 10 a.m. in San Francisco, and 10:30 at night in Mumbai. Greetings, good morning, good afternoon, and good evening, depending on where you are in the world today. My name is Patrick L. Young. The IPO-VID live stream, Series 15, Episode 2, that's Part 86, starts here. And where else can we possibly start other than reviewing the news story of the last week in the parish of exchanges, FTX. 22 days have elapsed since we started our BitCarnage story, noting FBX may be held below the waterline. A remarkable tale of hype, hubris, and indeed reality biting the cryptoverse. I have to say, on behalf of Exchange Invest, we're proud of our team that have been ahead of this story for 3 consistent weeks. This is the week, incidentally, when the New York Times Deal Book Conference will include none other than luminaries of the world of central banking, all sorts of wildly important financial people, and Sam Bankman-Fried. Most presume that he's going to be appearing at distance over Zoom from the Bahamas, far, far away from the long arm of US law. On the other hand, Turkey, where FTX had a major hub, is now eagerly investigating Sam Bankman-Fried and the whole fraud. Given a choice between Turkish prison and even federal supermax, well, I wonder which side might be chosen. But then again, with all those friends that were bought in high places, we're all cynical enough to reckon that SBF is unlikely to be troubled with jail, even if his fraud was worse than Enron, according to some measures, and indeed, despite his management ability arguably being insufficient to tie a toga. Meanwhile, the CEO of Binance, CZ, he says, don't fight crypto, regulate it. Part of his Damascene conversion as white knight of crypto during the course of the past month, which leads immediately to the question, why did Binance fight regulation for so long? And actually, remind me, where is the Binance headquarters once again? Still in crypto land, the cult of Bitcoin maximalization. Looked at FTX, it blinked and thought, ooh, let's buy some more Bitcoin on the dip. Thus, we saw this week in Forbes, 20% owned by Binance, we hasten to add, a stunning prediction, 1 million Bitcoin by 2030. If it's true, it means that the central bankers have really lost the inflation battle. Finally, today for our introductory segment, some touching festive moments from the one day off where Americans don't say happy holidays. Remember, as Exchange Invest noted, the big event of the past month in crypto is not the FTX fiasco. Rather, it's the success of the SEC strategy to gain a Howey test precedent, meaning a token is a security, where LBRY failed. That resulted in a rather spectacularly rude tweet of Thanksgiving greetings between LBRY and the SEC. On a very, very sad note, let me also begin this by saying our condolences to the family of Robert Woodthorpe Brown, a fabulous master of the world traders, frequent viewer of IPO-VID, and a great supporter of world trade. Robert, we miss you. R.I.P. Our guest today, ladies and gentlemen, is Professor Balaji Prabhakar. We're going to be talking about accelerating the cloud because Balaji is the CEO and co-founder of Clockwork Systems, building time-sensitive software solutions for the cloud computing infrastructure and distributed systems. He also happens to be VMWare Founders Professor of Computer Science at Stanford University. Previously, Balaji was co-founder and chief scientist of Urban Engines, acquired by Google in 2016, which developed a new type of database mapping objects in motion. Balaji, welcome to the show. Where in the world are you today?
Well, I'm in Las Vegas, Patrick. Here for a conference. Amazon AWS has its reInvent conference. I'm here to meet some folks in this conference.
What a fabulous venue to be in the midst of Las Vegas. And I'm sure the weather's a lot more pleasant than it is in incredibly wet and humid, stormy Valletta this evening. So tell me a little bit about yourself. Where do you come from originally, and how did you manage to get into this wonderful world of technology?
Well, I grew up in India, and my degrees are in electrical engineering. My bachelor's degree was from the College of Engineering in Chennai, now Madras then. Then I went to get a PhD at UCLA, also in electrical engineering, and began to work on networks, initially algorithms and theory of queuing networks, then packet switch networks, switch design, routers, that sort of stuff in the early part of my career. And then more packet transport protocols, standardization efforts, and so on. And then now, of course, it's all cloud computing and infrastructure for such systems, cloud systems.
Phone is off, and here we are, powered this evening by cloud computing. When I remember to turn my microphone on, apologies for that, ladies and gentlemen. Let me also just say good evening to some of our stalwart regulars on this show. Hello, Les Calvert. Good evening, Patrick Balaji et al. And good evening as well. It's lovely to see you this evening, Les. Good evening to Peter Secon. Evening all, says Peter. I hope Ari is very well this evening, Peter, and you're having a great evening. So, tell me, Balaji, you came then to the USA to study for a doctorate. Did you actually return home or did you stay in the US?
Well, I went to the UK, in fact, to Cambridge University and Bristol, Hewlett-Packard Labs. They had a joint institute called the Basic Research Institute in the Mathematical Sciences. I went there to do a postdoctoral, I was a postdoctoral scholar for 2 years at BRIMS. And then I became an academic. First, I was at MIT for a year and then moved to Stanford around 98. I've been there since.
Fabulous. So you've been at Stanford for quite a long time. You managed to go through the whole first .com bubble, which must have been quite spectacular to view from the academic perch of what was going on around you.
Yeah, it was a bit of a crazy time. I mean, networks had unleashed a lot of both real and somewhat irrational, as they called it at the time, exuberance. For researchers like myself, it was a really great time to be in Silicon Valley. Great time to be working with companies that like Cisco and stuff that were exploding, and part of the infrastructure building effort of the internet at that time. And a lot of the early work I did was in the components of networks like switches, routers, load balancers, web caches, that sort of stuff, algorithms for making these systems be highly performant. And so it was very exciting, as I mentioned, as a researcher and an academic. And of course, in the real world, in addition to being a resident of Palo Alto and seeing housing prices, and just everything else actually just go bananas, was it was a wild ride. It's always nice to watch that sort of thing from the outside. It would have been a little too much for my sort of temperament to get caught up in that sort of activity. But yeah, it was a crazy time. And then, of course, the .com bust happened. But Silicon Valley is resilient. I mean, the pick up and go. So that's the first sort of thing I saw up front, up close, actually.
So what then drove you into the idea of becoming entrepreneurial in your own right?
Well, I think after working for about 7 years or so, 6 years or so, in the academic sphere, I had an opportunity to take a sabbatical. And I thought, I'd either go to Berkeley there's an institute there, Mathematical Sciences Institute, or MSRI, Mathematical Sciences Research Institute, or go, consult with some company like Cisco or so. I ended up doing both. One day week at Cisco and a few days at the Mathematical Sciences Research Institute. And I just got closer to the folks who built these systems for whose algorithms I was designing. And I thought, this is exciting. So, I took my first sabbatical, joined a startup. I wasn't a principal. I was actually just a switch architect for that in that startup, Nova Systems. And then that was, quite exciting. It led me to doing not just the switch design for what became the switch algorithms and line card algorithms for Nexus 5000, Cisco's 10 gigabit per second Ethernet switch, but also I ended up working on some IEEE standardization efforts. And so that was really quite, instructive, informative to see how what we do in academia translates into the real world, into practice. So that was great. And so I was able to get a more rounded feel for my area of research.
Fascinating. So they give you a more rounded feel for your area of research, but somehow or other you couldn't stay away. So what drove you then to create this fascinating new technology that you sold on to Google?
Well, that was it was somewhat of a lark. I mean, this was nothing to do with computer networks. It was actually to do with road congestion and transportation networks. As you know, England, London, and Singapore, and a few cities like Stockholm charge levy congestion charges. In other words, if you're a commuter and you travel in the peak hours, you pay a surcharge. And I was stuck in a really bad traffic jam in Bangalore in December 2007. And discussions with folks at Infosys, the company in Bangalore, which is headquartered in Bangalore, it's a multinational, led to just talking to them about traffic and their commuters getting stuck in traffic and so forth, led us to do a social experiment, which was what if we paid people money to commute in the off-peak time? So instead of charging peak time commuters, how about we try to incentivize off-peak commuting? And this led to a really successful, sort of behavioral economic style project where we had the commuters of Infosys, the Bangalore office. There were a total of 20,000 of them. And we devised a system of lotteries, etc., and then found a way to take a small sum of money, but make it meaningful for the winners of these prizes, sufficiently interesting to all participants, so that enough of them would come travel in the off-peak time. And that led to further projects in the U.S. The government, U.S. DOT, funded a project at Stanford, and a further project in Singapore with their train commuters. And so by the time these things got going, we began to understand transportation networks in a very different way. Namely that suddenly there's GPS, people have smartphones, buses and trains, especially buses and taxis, were equipped with GPS. So you could, think of it as a system where you could track the progress of these systems, see where they're stuck, how to, route them, how to get more efficiency out of a transportation network. And of course, this is both from the capacity, namely the vehicles, as well as incentivizing the commuters. So there was a sort of two-sided problem, one on the demand side and one on the supply side, and how to make demand morph to fit the supply and how to improve the supply, the quality of the supply. So those problems became very interesting. And when you start doing this, in 3 or 4 different places, it leaves the purview of a university research project, because now you have actual commuters in cities, and that you need to, have a program for them, and that led to the start of Urban Engines. And so it was an exciting foray into the world of transportation networks and incentives, a lot of behavioral economics. We built some what we call nudge engines, and also looked a lot of big data of the urban mobility type. So yeah, it was technically exciting and socially very meaningful.
And so Urban Engines itself essentially drove itself, pardon the pun, forward from these transport network research projects you've been doing. And then what did it actually create?
So 2 things, right? So on the one hand, there was this incentive program that, you could, and we did run in Singapore, initially the 6-month Stanford project, then transferred to Urban Engines as a incentive program that we ran on behalf of the the train system in Singapore, the subway system,
Mm-hmm.
where we created essentially a frequent flyer miles equivalent program for public transit commuters. So we wanted to make people loyal to the public transit system. And like airlines do, we gave distance-based mileage or kilometerage points. And if you happen to be traveling in the off-peak time, off-peak shoulder times, you could earn more points per kilometer. So directly improving the engagement of a commuter with the public transport system, as well as an extra bit for nudging them to the off-peak shoulder times. So that was one thing that we devised, ran for a few years. In fact, up until the acquisition of Urban Engines by Google in 2016. So from 2012, January, 6 months, a Stanford project, then taken over Urban Engines until 2016. And the other side of it was the data, building a database that allows you to query, to quickly, to take all the raw GPS data that comes in and to put it through a process of healing and curing, because points could be missing. Sometimes a bus would look like it's temporarily running parallel to itself because you couldn't get a GPS fix on this road. Systems would actually snap the bus to a road that is parallel to the road that it's actually on. So things like this. So a system for ingesting, healing and curing mobility data, and also making queryable. Okay.
Mm-hmm.
So how many people are traveling on this route today? And what was the speed of the vehicles, New York City taxi cab vehicles? There was a big data released by the New York City Taxi and Limousine Commission in 2013 and 14, I believe. We had access to everybody. It was a publicly released, so we had access to it as well. So you could look at things like that. Where do people get picked up from? When they were going to US Open, what parts of the city were taxis coming in from, or leaving to from the US Open stadium to go back, things like that, things that you could run queries. And so that's basically the two sides of the equation: incentives and an analysis of urban mobility.
Fascinating altogether. And so then Google acquired the company. What did they do with it subsequently?
Well, it sort of went into maps, which was the right sort of area for it to belong to. And so the technology and the team got woven into the larger maps and data analysis efforts at Google to do with urban mobility, and that's basically that.
Very good. And that was from where you then developed this new kind of database that was mapping objects in motion, which we can see to this day in Google Maps, which we were using just this morning around here in Valletta. So very interesting. What happened then, and what made you move to the next stage of your career?
Right. So one of the key projects that we were working on as urban systems was the following question. Take a city, whether it's London or Singapore or Washington, D.C., take a city and look at the subway system. Most of these places have electronic cards that commuters carry that they use to tap in at a train station where they start their journey and tap out, at the destination station. And in between, they may have interchanged. In between, they may have waited for some friend to meet them at some intermediate station, etc. So, in other words, we have here just the tap in, tap out card, payment card information for this system. The system being the system of trains and the passengers that these trains are carrying, together. But the question that we were interested in is, from this tap in, tap out data, could we analyze that and reconstruct the movements of both the trains and the passengers? So, for example, here's one way you could figure out when a train was at a station. When a train comes to a station, all the people that get off the train typically hasten to the exit, and all the tap outs that happen at that station happen in a short period of time. So it'd be a bunchy tap out. And then there'll be a gap until the next train comes. another bunch of tap outs will happen. So you could simply look at these bunches and say, okay, first train, second train, third train, etc. As you look up the time axis, let's say. You could also say when this train that you're looking at this station now was at the previous station last, because if you go back to if you go to the previous station, and then there would have been a bunch of tap outs there. So you could actually follow the trajectory of trains by looking at these bunches of tap outs. And now you could say, okay, if I can reconstruct the trains, then let's say, a commuter got in at station A, got out at station B. I'd like to know what train they most likely got in on. So you again work from backwards. So you look at what train they tapped out at station B, and then now you know which train they belong to when they got out. And if A and B are on the same line, you can figure out which train, when that train picked them up at station A, right? So you could work everything backwards. And that's what we did. So this general idea that when you have a network and you have observations of the network only at the boundary of the network, and then the question of can you say what happens inside the network based on observations at the boundary is called network tomography. It's very similar to tomography, where like an MRI system where you're looking at a 3D object like the human brain or your knee or what have you, and then you have 2D slices and then you're stitching together. So similarly, you're looking at a dimension less, and from that you want to extrapolate and figure out what happens everywhere. So now that was what was exciting, technically very exciting project. And when I came back to the research world and back into my sort of area, namely computer networks, the same question came up. So if I'm looking at a data center and I know when a packet entered the network from the server that emitted it, and when it was reached the destination server, so I know when the packet entered, when it exited. Again, similar, tap in, tap out. Okay. Then can I figure out exactly how long it spent in each switch on its path? And so this is sort of a very interesting question. You can't do anything with one single packet, but with a large collection of packets, you could solve this. And this is what we did. And so to put an immediate question that jumped up for us was in the world of humans traveling in an urban environment, the clocks at the station at which you enter and the station at which you exit don't have to be synchronized very accurately. They could be off by a few seconds. Your journey time is 20 minutes or half an hour at least, typically. And so, if you're off by a few seconds, you haven't really lost much information. Over a 20-minute interval, loss of a few seconds of accuracy, it's not going to hurt you. However, in the world of data networks, it is possible that you have the destination clock. It could be that you're tapping out, with a value of time that is smaller than the tap-in value, meaning if the travel time is down to a few tens of microseconds or half a millisecond, and the clocks are off by roughly that amount, then you have nothing. You can't do anything. So we had to find a way to work on synchronizing clocks. So anyway, that led to a whole bunch of research, starting with this question from urban systems, tomography. Can we do that for data centers? And then that led us to doing clock synchronization and its consequences.
That's very interesting. And in fact, of course, clock synchronization was a huge problem that the Industrial Revolution actually drove forward, because when they built the railways, even a relatively small country like the United Kingdom, you had issues because localized time was quite a factor. And once you started going from the south of England to the north of England, you quite often found that the clocks were 15 minutes different when you got from A to B, which caused all sorts of problems with the unification of the network. Okay, so we're talking about this whole clock synchronicity issue, and certainly I can think of lots of things that are related to financial markets here, as we're discussing with Balaji Prabhakar, accelerating the cloud. Presumably, we're now at the aha moment, and that's what drove you to create Clockwork Systems.
Correct. I mean, that the idea that time is an important quantity in any network. You've given an example. There's a very good book that came out many years ago called Longitude by Dawa Dava Sobel. You may have read it. It was a brilliant book. And that was used for, figuring out which meridian a ship is, so that, they could use clocks to figure out where you are, let's say on the Atlantic Passage, as an example.
Mm-hmm.
And so when you come to the world of computers and computer networks, as well as distributed systems, clocks have a very important role to play. In other words, if a distributed system, such as we have in the cloud, is a cluster of machines that a user is using to perform some higher level task, so they're all coordinating. And often, if it's a system of the database type or a distributed ledger, what order are events occurring? Because events are occurring at different nodes. What is the order in which these events are occurring? Determining that, or coming to a consensus on that ordering, so that this problems like database consistency, etc. They're key questions. And what has happened is, in the early days, let's say if you look at the late 60s and early 70s, when packet switching and distributed systems respectively were in their infancy, because circuit switching was the dominant form of communication prior to that, as was mainframe computing the dominant form of computing. When packet switching and distributed systems were in their infancy, an important and rather astute decision was made by the founders of the fields to let go of clock synchronization. It is not easy to synchronize clocks over a jittery network. Let's not worry about that for now. Let's assume the clock's not synchronized. So then the fields evolved to cope with the lack of awareness of time or a common clock by evolving very clever, very sophisticated protocols like message passing protocols to determine what is the order of events. The order in which events occur doesn't have to be the exact order in which they occur in time. It is sufficient that all the nodes agree that this is the given order. Okay, and so that's an example of something that's called consistency. Right?
Mm-hmm.
And so then same thing for packet switch networks. So for about 50 years in the world of packet switch networks, we've always said the time taken to go from node A to node B is equal to the time taken to go from node A to node B, and for an acknowledgement to come back from node B divided by 2, meaning time from A to B is round trip time divided by 2. Because I can't compare the clocks at A and B, they may not be synchronized, but I can always certainly look at the time at clock A, okay, for measuring duration. So these sort of ideas have been used successfully, in fact, to give us the global internet and now cloud computing and all these stuff, all these other things. But we're also now running a lot of the real world out of the cloud. More and more, especially the pandemic has moved certainly a lot of entertainment, a lot of gaming, a lot of retail banking has moved to the cloud. A lot of like soon enough, self-driving cars have always been just over the horizon somewhere. But if you were to consider running them from the cloud, you need some notion of time sensitivity. Now time is becoming super critical, and it is not a notion. It's not notional. It's actual, right? So that's what Clockwork Systems and our research was actually addressing, and we're trying to build time-sensitive systems and applications.
Which obviously, of course, brings us directly to the world of financial markets, because, of course, in this series, well, just what was it, episode 75, we had Guy Melamed and Magnus Almquist of Exprey, and they were talking about building exchanges and trading systems in the cloud. Clearly, I mean, in this day and age, it's relatively easy to upload anything into the cloud, but building things cloud native becomes very, very different to how it might have been coded when it was in the basement of or somewhere else within the corporate headquarters, for example. How does what you do ultimately help and impact when we get to particularly time-sensitive activities such as financial markets?
Right. So at the core of any financial exchange, if it's an electronic exchange, is the sort of trading infrastructure, which, as you know, consists of a matching engine and a set of gateways to which traders are attached, and trade. They place orders, which pass through the gateways and get to the matching engine, and then buyers and sellers meet with their orders at the matching engine, and when the bid and ask cross, a trade occurs. Right? Now, it is critical. This is covered in the general category of fair access, that the time taken to go from a gateway to the matching engine be exactly the same, no matter which gateway to matching engine pair you're looking at. Okay, so there could be, let's say, 50 gateways. From each of those 50 gateways to the common matching engine, the time it takes for an order to traverse that distance, separating the gateway to the matching engine, has to be exactly the same. This would mean that the exchange is fair. In other words, if you are a trader and you observe a market event and react to it quickly, then your reaction is ahead of, let's say, another person's reaction. So you place your order first and the other person places it second, then they shall not overtake you at the matching engine. Your order shall get executed first. Okay.
Yep.
So this is basically the same fairness that you have in, let's say, quiz shows, where if I press the buzzer first, I should get to answer the question first. Okay. And so this sounds very easy, but it's not very easy to build in networks. So exchanges go to great lengths to make sure the distances from gateways to matching engines are nearly identical or exactly identical to the best limits of technological abilities, to ensure that fairness is guaranteed. And they verify that this is true, and they publish numbers and stuff showing how fair their exchange is. And these are fairly bespoke networks. They're not easy to do. Right. Now, if you take this system, it's also a distributed system, because there are trading nodes, and there are matching engine as a node, and so on. And then you want to move this to the cloud. And the reason that this is very interesting is, you get a large scale. You don't have to, pay a lot of money to sit at a colo facility. There's a lot of interest in trying to move exchange to the cloud. And the question now is, in a heterogeneous environment like the cloud, how could you guarantee this? And that's where clock sync and time sensitivity come in directly. Okay. And the gateways to matching engine distances are not equal. How can they be equalized? Well, the question is not to equalize them, by stretching the wires or something. It's more to add, a little bit extra time to the gateways that are more proximal to the matching engine, so that their orders are delayed just enough to ensure first in, first out service across the. Okay. So it's a technically it's a very, very interesting question. Not easy to build these things, and that's where viewing financial trading systems as a distributed system where timing is very critical makes all the work that we were doing become relevant and applicable.
It's absolutely fascinating, because obviously we've had a number of issues in recent years, and actually one of them, I think most notably the National Stock Exchange of India, where I can recall going to their incredible internal data center and standing there, and it was like something, the last time I'd seen a room like that, it was before it was fitted out. I think Tom Cruise had been dangling precipitously just a few inches above a hazmat floor that had some sort of a touch screen. This was before it was built, because when it was 3 or 4 stories ready to be kitted out when I saw it about 10 years ago. And obviously they had an issue, because it looks as if they ended up giving people priority for their order flow. And it becomes really, really fascinating to me, because, for example, you mentioned the fact that it's difficult when you've got one clock and another clock on different pieces of kit. Let's use a very untechnical word here while we're talking about accelerating the cloud. But you have different pieces of kit with different clocks on them. Synchronization, therefore. So do you have to synchronize all the clocks in the whole network, or is there a way to use the ABBA return time from a central node in order to work out that clock time and equalize things?
Well, if the answer is that if you're interested in synchronizing, let's say, 10 clocks or 50 clocks, so long as you can run software on them, you could directly synchronize them without having to synchronize the switches that connect these nodes. You can do it directly. That's sort of our approach, was to try and do it in what we call the edge-based way, without touching the network. There are standards that involve the network, namely the IEEE's precision time protocol, involves the switches and conveys time using the network itself. Okay, so that's the other way. And so if you want to just go to a large-scale cloud and computing environment, and where you have millions of nodes, and you want to synchronize just a few nodes that you're interested in, you could do this edge-based way of doing it. Right? And so that's what we've been doing. Our method is a software-based method for doing clock sync.
So when you come to what you're doing, I mean, you synchronize the clocks, and then I suppose my brain starts going into motor racing mode here. It sounds to me like, in one sense, you've got the Indianapolis 500, and then you decide to have those European Formula One cars on it. So you put a big chicane in the middle of turn 3 at the point when the Indy cars are going at 220 miles an hour, and suddenly you have to accelerate the European cars down. Is that essentially what happens? I mean, you produce a sort of a degree of chicanery inside the network by software in order to manage to equalize the timings?
No, the way the clock synchronization algorithm works, and it's published, and so I'm going to try and sort of give you the main highlights. I mean, in other words, the details are out there. The main idea is that you synchronize clocks by processing the timestamps data. So if you and I are clocks, and we exchange probes, these probes carry timestamps. And if let's say 50 clocks that you want to synchronize, they probe each other, they exchange timestamps continuously. And these timestamps, when the data is processed, allows each clock to figure out what is the offset and the frequency difference between itself and the clocks that it's exchanging probes with. And then a central coordinator then works out, based on these sort of local estimates, what is the global offset of each clock with respect to a given reference clock. Okay. And so that's the step one, meaning that's clock synchronization, period. Now, to use it to equalize travel times between nodes in a network, the way you would do that is to say, if some packet took a shorter period of time to go from node A to node B than was required, and you had a requirement, let's say that it should every packet should take precisely 15 or 20 microseconds. Let's say 20 microseconds to go from node A to node B. And if some packet ended up leaving node A and coming to node B in 17 microseconds, then because the clocks at A and B are synchronized, it says, I left node A this time. And that time when the clock at B looks at its time, it says, okay, that was 17 microseconds ago. You're not allowed to enter yet at node B. You sort of wait in this holding area for 3 microseconds, at which point you can then enter, right? So this idea of when the wires are not long enough, you have this sort of holding areas. We call them resequencing buffers or hold and release buffers. That would give you the ability to equalize times and allow for determinism in an intrinsically sort of random sort of environment.
That's really fascinating. So we're discussing here accelerating the cloud, and I think therefore I'm beginning to understand the holistic picture. So what you're saying is, by using your technology as software on top of the existing network, whatever that network might be of an exchange, you can essentially deliver an opportunity where they can still have ultra low latency trading, but essentially it's a level playing field for everyone according to when they put their order in.
Yes. I mean, That's correct. That's a good summary, Patrick. And by the way, this is happening in sort of co-location facilities, training and facilities now.
Yeah.
It is what, you know, extra pains have been taken to build these sort of systems. All we're trying to say is that you don't have to worry about doing similar things in the cloud. You could technologically solve the problem in a different way potentially, right? And the way we're proposing is the one I've just summarized. But I think this, if you don't mind, there's something else to the way we were talking earlier. There's something more important, let's say, that I want to just mention.
Go ahead.
Going back to this sort of idea that clocks were let go of, so to speak, in the early design of packet switch networks and distributed systems. This is around late 60s and early 70s. Very astutely, by the way, if people had said, "Oh, this field won't go anywhere until we synchronize clocks, find a way to synchronize clocks," it would have just stayed there for a while, because some of the techniques that we use are creatures of the modern, ML type era. So these things weren't available. We couldn't have solved the problem that we're solving, let's say, in the late 90s, potentially. Things have come, adjacent technologies now developed to a point where we can do it. But let's just think of what is it that should clocks have been synchronized, and we're now back in the early 70s, and the fields of distributed computing and package networking are just taking off. What could we do differently? Could we design some of the systems differently, perhaps making them more efficient? Could we build new systems that we didn't attempt to build because we didn't have accurate clocks? So that's a sort of higher level question, and really what motivates our work, certainly the research work we're doing at Stanford. I mean, I'm sort of keen to mention that because the financial application came at us from out of nowhere. I mean, we didn't know that clocks are so critical for financial trading platforms. Our motivation was really to look at clocks and see if we could synchronize them and then use them to build more efficient or new sorts of systems, time-sensitive systems. Does that make sense? Because I think it is unlikely for a CS group, or a professor with his colleague Mendel Rosenblum is my collaborator, along with all the students we worked with, to take up a question that is very intrinsically Chicago, New York, or London type. In other words, financial. Those things are happening somewhere else. From our point of view, we are over here. But it was a beautiful coincidence of things that we are now happy to have become aware of this financial thing, because it is a really everything becomes more concrete. It becomes a pressing question, and so I just want to give you our motivation as being distinct from the financial trading part initially, at least. Of course, now we're working on it also.
But no, now you've come to realize how exciting and interesting this is, where people value those microseconds, and indeed also the integrity of markets live and die by offering a fair and reasonable access to everybody within that marketplace. So what you have got with Clockwork Systems at the moment is therefore a relatively simple fabric of software that can be deployed, which therefore means you don't actually have to change the network as such. You're essentially network agnostic. Is that right?
Yes. I mean, yes, in quotes, meaning, by and large, if you think of any typical sort of computer network where there's a bunch of computers at the edge and a network of switches connecting them, yes. Could it include Wi-Fi systems? Could we do this inside a home? Potentially, but Wi-Fi routers and stuff may or may not be programmable. So that's why I want to say essentially yes, but the computer networks are a very large category of system. So exceptions.
That's really, really interesting. So therefore, with Clockwork Systems, how are you moving that business forward now in any domain, but particularly obviously with reference to the financial domain?
Well, the financial domain, really it's the case for accurate time and accurate clocks. They have made it themselves. And so with them, we are, mostly working on things that link sites that are far apart around the world. I want to know. I'm trading in Frankfurt or London, and I want to know what this when this piece of market data was emitted in Singapore or Hong Kong. Exactly, then I can tell how long ago it was emitted. It bears this timestamp. So if the clocks are synchronized in London or Frankfurt with the clocks in Singapore and Hong Kong, you could sort of answer these sort of questions. That's one way, connecting disparate sites of a trading system. The other way, of course, is working with folks in the cloud native exchange like the crypto type or others who run. Even conventional trading firms have increasingly taken to the cloud. In the usage of the cloud, they resemble more or less other cloud users. In other words, the fact that they're financial firms may be one aspect of it, and they may actually want clocks. But the other aspect of it is that they could be just like anybody else, like somebody runs a large batch processing job. And there, because of this takes us away from pure clock sync to new ways of managing congestion in sort of cloud environments based on the use of accurate clocks. There's something else that we've developed. And so it allows us to minimize packet delays and packet drops. So this is something that is generically interesting. And in a nutshell, what it is that, the way to think of a network at the level of the pipes, the wires, and the buffers is, think of it as like tubes through which you're pumping data. And once in a while at a switch, there could also be a little bit of a buffer that, the water makes sort of when it's flowing. When there's more water arriving at a junction, like a switch, that can be drained by that switch, some of it will sort of rise and form, get buffered. And that buffering can lead to delays in the few milliseconds level. This is commonly happening every day in the cloud. With what we're doing now, we could remove those delays. We could get rid of those milliseconds of delay. And for many time-sensitive applications, this is very interesting, very critical. So that's more general than just the trading application.
That's really, really interesting. And then I suppose one thing that I've been thinking about, because you mentioned it at the start of the show, you were talking about sort of distributed ledger technology and applications. But, well, perhaps this is me showing my ignorance here, but isn't it the case that with a lot of distributed ledger technology, I mean, actually the issue is that it's relatively slow. I mean, it's difficult to produce it in low latency. Or were you referring to it in terms of the whole clock syncing exercise enables your network to simply have better data rigidity?
No, I was referring to it as if you look at a ledger of the Bitcoin type or something,
yeah,
permissionless ledger. The whole puzzle solving and proof of work, proof of stake, all of those sort of things, is to determine what is the order in which entries are made in this ledger. Because, different ledgers are, having transactions going on. And the essence of a distributed ledger system is that all ledgers shall have all transactions occurring in the same order. That is the whole central question. Now, in the world of permissionless ledgers, the right to decide what is the order of events is really what people are, doing all the mining work or other types of work to get to the privilege of deciding what is the order, right? I wasn't referring to that. I was referring to simply that there are crypto exchanges, like not different from sort of conventional exchanges like New York Stock Exchange or NASDAQ or London Stock Exchange or what have you, where cryptocurrency is traded, potentially, directly at one kind of cryptocurrency for another, or perhaps hedged as a hedge, against or with something else as some other asset class. And so, when you come to that sort of a system where you're trading, then that resembles a conventional exchange, and that's sort of crypto exchange like with the FTX and Binance type that you mentioned earlier. Those are not where that's not what the miners are doing. That's mostly traders.
Yeah.
Now, when such things are done electronically, when the trading happens electronically, it's very similar to any of the conventional exchanges, except that conventional exchanges are have been around for long and very highly regulated, and everybody understands very precisely what's happening there. At some point, I think crypto exchange will get there. That's one aspect. But the other aspect of it is, in the world of permissioned ledgers, that is, there's the participants are not supposed to be they're known. They're not expected to be malicious or fail in some Byzantine ways. Then you could, IBM has this sort of open source thing that they put out called the Hyperledger Fabric. And these sort of systems, again, also have to decide the order of transactions. And they don't do it by solving puzzles. They have an ordering system built in. And that is done, sort of proposals are made, it goes in rounds. When you have accurate clocks, that problem of deciding ordering of events in permission ledgers can be sped up. Okay, you don't have to take as long. So in fact, it was a project that a student in our research group did at Stanford. He ended up calling it clock chain. So to sort of emphasize the fact that clocks were used to speed up the ordering of events in permission ledgers.
That's very, very interesting altogether. And so to go back to Clockwork systems as a whole, can you utilize Clockwork systems on, say, if there's an exchange, if the market is using a public network, like, for example, the World Wide Web, or does it have to be on a closed network of some form, such as the professional exchanges use?
Great question. I mean, it really comes down to leaving aside the critical aspect of security. I mean, that's really, if you think of a network as simply nodes connected by wires, and one of these nodes gets nominated as the matching engine, and the others are, let's say, nominated as gateways, or some of the others nominated as gateways, and then you're still interested in minimizing the gateway to matching engine, or equalizing the gateway to matching engine times, then of course it can be the wide area internet. It doesn't have to be something where it's a more challenging problem. You may have to hold and release for longer periods of time, but in general, in principle, nothing is different. It's just wires and nodes. The reason that trading fundamentally, there is a notion of time that enters in these things. As you know, if you have another way of communicating, for example, the microwave, systems that people use or that are available to communicate information on price over long distances faster than is possible over fiber. Things like that, are what you're looking to. You may be competing in such other systems. So, but in principle, it's okay. You can do it. Such an example already exists, by the way, if you leave aside the world of financial trading, but instead look at gaming, multiplayer games. It's very similar. Players and financial trading and multiplayer games actually are very close. I mean, you can view financial trading as one massive multiplayer game, actually, right? Where, again, players are responding to a common scene that they're looking at on a screen. And usually it's a first-person mover sort of advantage. And, if I'm sort of, let's say, shooting first or reacting first to grab something, then I should, get the credit for it at the game engine. Very similar. There are differences, of course, but this is done at a much wider scale. I'm sitting in my living room, potentially. You're in your living room, and we're typically a few tens of milliseconds away from the game engine, as opposed to a few tens of microseconds away from the matching engine in a trading environment.
That is quite intriguing altogether. And I appreciate the fact that, well, a notion of time sensitivity has overcome this particular live stream, because we could go on for ages and ages. So it's time to ask you that all-important final question as we talk about accelerating the cloud. Balaji, where do you think the capital market revolution goes next?
I'm not an expert on the topic, so I don't want to pretend to know sufficiently, enough to answer that question, with some serious confidence and authority. But I have seen proposals, for example, from Eric Budish, who's a professor at the University of Chicago, in the business school, for new types of trading, where trading systems, trading platforms, where it's not just a race, speed race. And he's got a proposal, and he's got his arguments. But equally, somehow I also feel as the technology is that the genie's out of the bottle. In other words, if there's a technological ability to do something, people will do it, and it is going to happen that way. And there is probably likely to be a speed race about all the time. But increasingly, when you get scale, when you go to the cloud, and you have not just 300 people again with whom you're trading, like as happens, let's say, in a large colo facility these days, that's probably even a larger number than colo facilities can handle. But let's say you now have 3,000 or 30,000 people in the cloud that you're trading with, then I think the whole game will shift to something more where it's more, how clever are you at understanding data? How advanced are your ML and AI type algorithms? Could you do things like limit order book reconstruction very cleverly and stuff like that? So this is that's one area I've seen some activity. The other one I like is also that smart contracts. People have talked about them. For example, something that one could do right now. Traders look for the right price, and so when they place an order, they sometimes cancel it and revise their order to either make the price lower or higher, depending on whether they're selling or buying, and so on, right? So these cancellations are required. Otherwise, you may end up buying twice the amount that you wanted, just because the previous wasn't canceled. So you could put a time limit on it. Because clocks are synchronized, you could think of smart contracts now as saying, I want to buy XYZ at this price, and my offer is valid at no more than this price, let's say, and my offer is valid between time, T and T plus some delta, and the delta could be a few microseconds. And so you could see this ephemeral I can quite easily see that happening because it's the right, next construct. So let me leave it with that. One larger scale AI ML coming in, and the other one being more at the level of wires and smart contract objects. Yeah.
What a conversation. Thank you so much, Professor Balaji Prabhakar. That has been the most incredible discussion, accelerating the cloud. I have to say, personally, I think my own data network is suffering a little bit of buffering and some congestion. It's going to take me a little bit of time to unpack the incredibly data-rich experience we have enjoyed. Thank you, ladies and gentlemen, for watching this evening. Thank you, Peter Second, Les Calvert. Thanks to the production team, to Mary, to Herminia, and to Jake. And congratulations, Jake, on the birth of Raven this week. Next week, we're going to be into the year in review, ladies and gentlemen. So I'm going to be running through some of the highlights of this incredible data-rich multi-gigabytes of information that we've shared during the course of the year. But across, I think it's something like 35 shows and 42 guests to date. It only remains for me, ladies and gentlemen, to say thank you very, very much for watching, and I wish you all a great week in blockchain life and markets. And thanks once again, Professor Balaji Prabhakar. We've been accelerating the cloud with IPO-VID.
Thank you, Patrick. Thanks for having me on the show. Bye.
You're welcome.